Hi, I'm Amir Hossein Mirzabozorg, and in this video I will talk about Comprehensive Abaqus Package Chapter 9 Example 1 2D and 3D Rolling Simulation. How to ask your video related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer a step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. This is the table of content for first example of chapter 9. Okay. Introduction, the primary solution for solving nonlinear static and quasi-static problems. The static general step is the primary solution for performing nonlinear static and quasi-static simulations. Also in the previous chapters, for example, in chapter 6, when I simulated tensile test, I used a static general step, okay, for doing nonlinear analysis. For tensile test, we had two nonlinearities. One, the plastic behavior, second, nonlinear geometry, okay, which is related to large deformations, and a static general step was successful in solving all of these, okay? Using the static general step, all of the sources of nonlinearity can be included in the simulation. A wide range of nonlinear simulations can be performed by using this step, but convergence issues may arise in some simulations, and the Abaqus standard solver will fail to complete the simulation. One of the most effective solutions for resolving these convergence issues is using dynamic steps instead of a static general. What are the dynamic steps? Dynamic implicit step and dynamic explicit step. Here I have mentioned two cases, mechanical problems and coupled thermomechanical problems. For mechanical problems, the primary solution is the static general step, and its solver is Abaqus standard. And for coupled thermomechanical problems, the primary solution is coupled temp displacement step, and also its solver is Abaqus standard. And the secondary solution for mechanical problems are dynamic explicit and dynamic implicit steps. The solver of dynamic explicit is Abaqus explicit, and the solver of dynamic implicit is Abaqus standard. So the solver of dynamic implicit step and the static general step are the same. And the secondary solution for coupled thermomechanical problems is dynamic temp disp explicit step. The solver of this step is Abaqus explicit. In this course, we don't cover this step. Maybe in the advanced Abaqus course, I will solve several problems using this step. For example, to simulate the hot rolling, we must use dynamic temp disp explicit step, because this simulation is highly nonlinear, and in this simulation we have contact and large deformations, and also material changes with temperature, and it increases the degree of nonlinearity of the simulation. And that's it. Please notice that here I have set secondary solution. Hello, Mr. Qasemi. Here I have mentioned secondary solution. Okay, it means that first we must try using these steps, and then if we face convergence issues and we cannot solve them, so we must switch to these steps. Okay, they are alternatives. And some other issues that force us to use secondary solutions. But if we don't want to do trial and error, we can use another procedure. We can use this formula. The average speed of the rigid part or rigid punch must be less than 1% of wave speed. And the average speed of the rigid body is equal to the distance of its displacement divided by time period. Okay, and also we know the value of CD. For example, here I have calculated them. For that example, okay, for that example, the aluminum plate, CD is equal to this value, and displacement of the punch is 0.2 meter. So displacement of the punch divided by T must be less than 1% of CD. So the time period of the step must be greater than 0.004 seconds. Okay, so the minimum allowable time period is 0.004 seconds or 4 milliseconds. But if I want to be conservative, I multiply it by a factor of 2.5, so the time period will be 10 milliseconds. For accuracy, the calculated time period is multiplied by a factor greater than 1 to increase the time period and make the simulation more quasi-static. And here I have entered 0.01 for the time period of the step. And this is the force displacement curves for all 4 simulations. You can see that the light brown one is the static general one, and also the pink one is obtained using mass scale, and the dark brown one is calculated using loading rate, and the blue one is obtained using the dynamic implicit step. Here you cannot see the light brown one because it is covered with the blue curve. Okay, it is covered with the blue curve, and they are almost the same. Okay, they are almost the same. Because of this, you cannot see it here. Okay, that's it. And about conclusions, the force displacement curves of the dynamic implicit and static general steps are very similar because they have the same solver. When you use the dynamic implicit step to solve a quasi-static problem, the solution will be so close to the solution of the static general step. The results obtained by Abaqus explicit and Abaqus standard solvers are similar. This means that the solutions are quasi-static and accurate. The problem is this. We have this thick plate. We have 2 rollers. Okay? We have 2 rollers. And it passes through the rollers with the initial velocity. And here we have it from another point of view. This is the first roller, Okay, this is the second roller. No, its shape is not good. And this is the this is the specimen. This is the workpiece or billet. If you see these pictures, you will find that we have two planes of symmetry. Okay, we have two planes of, no, it's not good. We have two planes of symmetry, and I want to use both of them. So I only model this part. Okay, I only model this part. And we have the dimensions here. And the depth. The depth must be larger than the depth of the billet. The depth of the billet is 20. I set it 40. Okay, I set it 40. And tools reference point, I put the reference. I can put it in both of them. For example, here. I go to property. I want to use the material property of the previous models. So I go to material library. I must create a coordinate system myself. No problem. I create a coordinate system, a rectangular coordinate system. This is the origin. This is the x-axis. This is the y-axis. Yes. And for mirroring, I will use this coordinate system. No. Global, no. My coordinate system. I use xz and xy. This is the full model. And see what happens. Okay. If you see here, we have such deformation along the thickness of the billet. But if you do it in 2D, as no calculation will be done in the Z direction, so this will not be captured. Okay? And this is the error of the 2D simulation. You cannot capture such deformation using 2D analysis. But 2D axis symmetric analysis is completely accurate, and it is used for modeling processes like extrusion. Okay, extrusion. For extrusion, axis symmetric modeling is completely accurate, but for 2D simulations like rolling, you cannot capture this deformation. Okay, and this is the error for the 2D analysis. And also here, if you see, we have such deformations. It's very interesting. Even in the other in the other, how can I tell, faces, in the other faces, if you see they are similar. And what is the cause of difference? That deformation in the z direction is the cause of difference, because when you assume it to be uniform, okay, it means that the billet is stiffer, but here it means that it is not stiffer, and because of this you can see that it is the absolute value of reaction force in the y direction in the 3D model is less. Okay, and which one is correct? The 3D one. The 3D one is correct. Okay, because we have accounted for the effects in the thickness direction. Okay, and here RM3 and also here we have the similar explanation. Okay, we have similar explanation, and that's it. This is the difference. And did you understand my explanations? Sina, did you understand? Okay. And so here maybe you have a question. Why the reaction moment curve and the reaction force curve are close, but the 3D stress field is not close? This is because of the sensitivity of stress to the mesh. We must use smaller elements. Also, the stress field will be similar. Okay, stress fields will be similar. And now I want to talk about yes, here this example ends, and now I want to go to the next concept. Okay, I stop this. How to purchase packages or individual chapters. Each of the packages and individual chapters includes CAE, JNL, and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers, and standards. Packages, specifications, and payment details are provided in the video description. Also, you can pay the cost of the packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. The cost of each chapter or package will increase after each update for new buyers, but those who purchase the package would have endless access to all the upcoming updates. This will make the content up to date for new needs and new problems which must be solved via FE simulation. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects, and we offer support in writing the modeling and result discussion part of your thesis, and we have consulting services for MSc, PhD positions or job interviews, and we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.